Okay, thank you very much everyone for attending this first academic 3D academic license users webinar. My name is Andres Diaz and I'm working for Thelen and Schurmans. In the last, let's say the last month, we have been organizing different kind of webinars, and we felt that the 3D academic license was one of the type that we should organize. So we are very pleased as the committee organizers for hosting this first webinar. Yes, Thelen and Schurmans is a company that has been founded in 1998. And since around the year 2010, we started developing of a non-hydrodynamic model called 3DI, for the ones that are not familiar. So yes, as a background philosophy, sorry, one confirmation, are you seeing my screen?
No, we don't see your screen, so you need to share your screen.
Okay, thank you. Sorry for that. I was starting to present without, yeah. Yes, I hope right now you're seeing my screen. So yes, so basically as a philosophy for our hydrodynamic model is that we are always trying to find an optimal balance between the accuracy and the speed of the hydrodynamic models. For doing this, we have been researching and implementing the best way to solve different kind of problems and in different domains. So example of this is like only 1D pure models or 2D models, or a combination between 1D and 2D, or also solving groundwater models. So this is our philosophy, to find a balance between the accuracy and the speed. Why this webinar? So basically, since our aim is to use the most updated methods to get the best results, we have been constantly collaborating between universities and research institutes. Also, we have been hosting in our headquarters PhD students and master students that currently, and also currently some of our staff, like Nikkei here present, are giving lectures, and they are invited in some universities to give talks. So for us, it's like an opportunity for like disseminate what we have been created with our hydrodynamic model, but also it's an opportunity to connect different research institutions. Finally, with this webinar, we also intend to understand which weakness and which possible improvements we can have in the 3DI model. As you can see in this image, the 3DI model has been used already in different countries around the world. So it's like very vast, the experience we already have in-house. So in here and afterwards this webinar, you will have this presentation. In the same, you will have this slide in which you can follow the instructions on how to request an academic license. For today's, we are going to have 4 presenters. Unfortunately, one of our presenters didn't make it to join the webinar. So the first one is going to be our first guest is going to be Miroslava Lukiyanova, and so on. We're going to continue with the program. Also, in this presentation that we're going to share, you're going to have some useful links on, for instance, how to use 3DI, some scientific publications we have done, and also future webinars that we are hosting in the house. So it's also very nice that you have these links for future research on our model and how to use it for academic purposes. Finally, if you have any questions, please contact us, contact my colleague Nicolette or my colleague Jonas. We are going to have also our emails. So as a first speaker, I would like to introduce Mrs. Miroslava Lukiyanova. She was doing a master thesis related with potential and modeling possibilities for sponge cities.
Okay, so at this point, I'm going to start my presentation. Thank you all for that you're here. During my presentation, I'm gonna short explain what is exactly Sponge City. That's we need for what is exactly blue-green infrastructure because it's connected. Then I'm gonna show you possibility study, and then we came shortly to evaluation and discussion. Green-blue infrastructure, it's like natural-based elements which are compared to gray infrastructure. Gray infrastructure, it's all we can see in our cities or beaten streets or concrete streets, asphalt, buildings, everything that could not absorb water. Everywhere where is used pipelines to absorb the water. Therefore, is green infrastructure, as you can understand from its name. Green means something natural-based, which make ecological value of urban space. And blue infrastructure, it's water surface. And blue-green infrastructure means some measure that connects natural green surface which absorb water or connects rainfall water with some natural blue surface like rivers or sea. In modern city, we could not stay without great infrastructure. That's why it's important for us to find the middle point which connects all of these parts of infrastructure, because in our city we have big enough buildings, a lot of streets, and all those surfaces we cannot just destroy. We should use it, but use it as small, clever, more green or natural. There's also other goals of blue-green infrastructure, like regulation of microclimate, reduction of urban noise or air pollutions, contribution to migration to impact of climate extremes, like, for example, urban floods or heat, buffering and regulation system for water and management, improve of quality life by reducing of urban noises or pollutions, but as well as heat or something climate extremes. And as well, it's like long-term perspective to solve our problems. On this graph, you can see as well how does works blue-green infrastructure compare to standard runoff. At the beginning of it was of raining, the intensity of it in the water could be much more than by standard runoff, but by the time infiltration shows up, that it's more useful than the standard pipelines. Sponge city, like say its names, it should work like a sponge. It should absorb, store, and filter water in the city. It connects some mixture of blue-green infrastructure, which is as well natural and natural-based. It was made first in China as an answer to climate changes and its impacts on the city. It's addressing to issues through creation of water management systems, as well as reducing the risk of floods, soil erosion, water pollution, and some similar problems which have modern cities and big cities. Yeah, goals and research questions. On my thesis, I should model an urban district of the city Dresden in Germany, where is the university, which is prone to the urban flooding in dry D. There is a small word because in year 2003 and 2014, the city of Dresden had a big problem with urban floodings. As well, during the using program and the thesis, I should analyze flood burn areas and their characteristic, implement sponge city measures, which are natural base, as I said before, evaluate the effectiveness of sponge city measure for heavy pluvial floods. Yeah, and invalid dry D for modeling and emulating such a measure, integration, and savage. Yes, in this point, we're gonna came to feasibility study. There was the area, like I said, some part of the city Dresden, which was used for my thesis. As you can see on those area, there's some big differences in high, like at the right side, there is a local mountain, so to say. There is 200 meter. The lowest point is the river, as you can see, river canal, which is blue on this topography map. For modern representation was using QGIS on base which is made 3DI. And for model, I made some layers and as well used schematization settings by DryDI. In QGIS, as QGIS layer, I mean raster data and vector-based information. In totally, I made like 12 layers and schematization settings, which was digital elevation model, like you said before, land use. So what you can see this picture on the left, Manning roughness value. It's the second picture on the right. As well, I've made infiltration rate, which was connected to the ground, which is in reality at this area, permeability, and as settings, grid, boundary condition, and 4 layers or elements for 1D element. So that was a river Weißeritz. As elements for it, I used levee, channel, cross-section, and as well boundary conditions. Here you can see which database I used for creation these parts of models, like a roughness or land use, and how they connected to each other. As well, I've made this impervious surface, but later I found out that this layer should be connected to the pipelines, so it was useless at my simulation. I've made like 7 variants of models or simulations to find out one would should the most accurate shows reality, and as well which would be the most useful for my thesis. I made a basic version, like you see, period of precipitation 33 and 7 mm for 60 minutes, which was detailed by all layers and schematization settings, which I said before. On this model, I've made as well extreme weather version with precipitation 55 mm for 60 minutes. To compare, I created simplified version. A simplified version, I mean there was no more raster base. Everything was written in a data schematization settings. There is as well precipitation like in the first version. I made as well an uncountable 1D and 2D version, which I didn't use the river as an extra element of 1D. simulation precipitation is exactly like a version before. Raw grid, which you can see in the table, the second table on this screen, there is raw grid space was much bigger than in basic version. And after comparing all those versions, which was the most accurate, on base that I built a second model, which with sponge city concept, where I made as well two rain simulations with precipitation based version 33.7 millimeter for 60 minutes, and one with extreme weather with 55 millimeter for 60 minutes. Yes, here you can see those settings that it was constrained rain, which would be not as accurate representation of real rain, but it was much easier for use these settings. All those numbers I've took from a German weather service, so it's a bit accurate, shows the reality. Here you can see the results of my first simulation. It shows like flood lines. It's a without zooming, it's pretty hard to find out what does mean it shows, but after zooming you can see that there is some arrows which shows with their color of intensity of the river of water. As well, I've made an other results of these simulations. You can see that after 30 minutes, how many water it would be connected on the plan, on the area, and there as well, there we can find out some problems area where are about 1 in 45 meter of water which are on the area. Compared to that, extreme version shows us that there are as well similar problematic zones of this area, and there it's stored water for 1 meter and 67 meter. A simplified version shows us that it's not useful to use it for such a big area, because it would be used as one big area with the same infiltrations as you can see that on form precipitation has no time series, there was used no roughness and no infiltration. It shows us inaccurate the model and simulation. Other was with raw grid. On this plan, we can better see the arrows, which shows us the flood lines. Nevertheless, it's pretty hard to find out what exactly they show us and find out where are real areas like parks, cemetery, and so on. And this part of simulation was a bit faster than other ones because of such a big grids. Nevertheless, it's not really useful. Yes, here to complain uncoupled 1D and 2D versions. It shows us that just after 5 minutes, there is a lot of stored water. which not shows us accurate the realities. It's impossible that after 5 minutes of simulation they would be stored till 2 meters of water level. As well, you can see on the right build the graph that the intensity it's out pretty big after just 5 minutes. So think that we find out that the most optimal way to create such a model and simulation, it should be pretty much yeah, like a based version. Like I said at the beginning, it should have many layers.
Miroslava, if you can summarize in 1 more minute, I can give you 1 more minute because we need to move on.
Okay. Thank you. Yes, as you can see here, I made like 10 measures of spongicity elements to build it on the second model. Here to complain, there's some building that you can see how exactly it should looks in the reality, which was built at the Copenhagen climate adaptation plan, as well as spongicity. And there we can find out that some problematic areas stored not as much water as on the basic version, as well as the spongicity concept with extreme weather. Here you can see that after less than 24 hours, the water is already absorbed. To compare, here you can see the basic version with both wetter versions, and even after 34 hours, the water is still stored, not absorbed. Yeah, there's not much time. Like I said at the beginning, what should do to us spongicity. Yeah, there it shows us many possibilities. It shows us some goals that you have already saw on the simulations. Nevertheless, there are some prospects that could be used in the future, like several network models, storage or pumping system. And for example, in whole simulations, there was not used evaporation, which during absorb and using such green blue infrastructure and spongicity elements could be till 20% of all stored water. Thank you for attention.
Okay, thank you very much, Miroslava, for your very interesting presentation. Does anyone has a question? If not, in here from one of our colleagues, she has 2 questions, Miroslava. The first one was, what was the resolution of the subgrid? And the second one is, how did you choose the refinement locations for the course model?
Yes, are those questions in the chat? Because it would be easier that I can.
I'm reading it out loud because she was writing me.
Okay. Yeah, could you please repeat the first question?
Yes, the first question is, what was the resolution of the subgrid? And the second one, which is like related, is how do you choose the locations?
Yes.
Yes.
Yes. I'm sorry, I can't remember how was it. Here you can see the resolution of first and second grids. The first one, it was like 6 quadrat meter, and the second version was 96 meter. And here you can see how was the settings for it.
Okay, and how do you choose the location? So basically, you will try to refine more on particular structures, or?
You mean all those area, or just problematic
Yes,
zone?
in general,
Because
how do you choose which locations to refine more and which leave it like coarse resolution?
Yes, I find out that after simulation that you can see on even of on this simulation results that there are some areas where it's stored more water, like till 1.45 meter, and it's 3DI live site. I've tried to give more time to find out how long will stay this collected water. And as you can see, even our 34 hours in basic version, in basic precipitation, those stored water still stays there. It would be not absorbed. And compared to this, you can see what happened after using sponge CT elements.
Okay, and the resolution of your raster was?
The resolution of my raster was here. You can see it's like yes, in Sponge CT concept I used the same resolution as in the basic version, so 6 quadrat meters.
Okay. Okay, thank you very much for your presentation, Miroslava. I do have one more question, but maybe after we finish it, I will make it to you if no one else has more questions. So we can pass to the next present. Sorry?
Yes, of course.
Well, yes. So our next presenter is Jaemun Tu. I hope I pronounced correctly. She's from TU Delft, and she's going to talk us about urban flooding in Yangon and the assessing of nature-based solutions. So I'm going to make you presenter now. Jen, let me 1 second.
Can you see my screen?
Yes, I can see your screen.
Okay. Thank you, Andre, and thank you. It's nice to be the part of the program today. My name is Jaemun Tu, and my current research work is very similar. The general concept of my current research work is very similar to the first presentation, and I am currently looking at the urban flooding in Yangon City and trying to see the potential simulation for the nature-based solution with 3DI simulation. So I would like to briefly introduce about myself. I finished my PhD from Yangon Technological University in 2019, and during my PhD, I also was a researcher at UTEP in 2016. And after my PhD, I work at Raychel DHB Myanmar company. And after that, I work as a water resources engineer at Waterbridge Myanmar company. And in 2022, I came back to UTEP as a researcher to work on the research work. During the past few years, I'm working on the flooding and drainage analysis with the hydrology and hydraulic modeling. So for today's presentation, I will mainly talk in 3 sessions. First is the introduce about the study area, which is Yangon City and its flooding causes, and about the development of the flood model in 2019 with 3DI. And finally, I will talk about the my current ongoing work, mitigation with the nature-based solution. So first, the Yangon City is the former capital city of Myanmar. It has highest concentration of people and assets, which is in the country. It is the economic center of the country. So if we look at the location, it is located in the country's southeast monsoon delta, which is built on the low-lying ridge surrounding the alluvial floodplain. So in administration level, it has 33 townships, and its municipal facility are arranged by the YCDC, Yangon City Development Committee. So if we look at the water system, the topography of the city is relatively flat, and the rainwater is drained by the gravity with a patch of drain and its river. And the city has three types of the city is prone to 3 types of flood. First is the pluvial flood, the heavy rainfall during the monsoon season, which is from June to October. And the next one is the fluvial flat. It has three main rivers surrounded the city. So it has a high discharge from this river. And finally, it has a coastal flats, which is from the sea. These rivers are the tidal, it has the tidal range. So the city has a tide twice a day. So Yangon is prone to this, mainly prone to these three types of flood. So obviously some areas are dominated by the flooding from the river overtopping, which are the township, which is close to the river, and some area experience flood frequently from the rainfall when it's coincide with the high tide. So to facilitate YCTC in the analysis of the Yangon urban drainage system under various conditions, in 2019, a flood model was developed with 3D and software. The team was led by the Raychel in DHB, and I was also one of the modeler. So I would like to present how we develop the model a bit. These are the main data that we use for the rainfall data. We use the station rainfall in the model area, which is a long record. And for the topographic data, we have the green area is the LiDAR survey data, which is a very good resolution, 1 meter resolution. And purple area is the raw DMs to fill the requirement of the model area. And we have the bathymetric survey data for the rivers. And for the drainage network data, we collected the drainage network data, and also have some survey to validate the data and fill the data gap. And for the land use, we use this 7 types of land use data to develop the model. So the approach is the first to deriving the catchment from DEM and creating the model extent and the boundary condition. For the grid data, for the 2D domain, we have elevation, bathymetry, elevation and bathymetry, and friction and the infiltration rate grid. And for 1D element, we have primary and secondary drain and other strata, and we add the operational mechanism. And after that, we calibrate and validate the model. And after that, we have simulate for different kind of scenario. So for 1D model, for 1D domain, we have pre-drain cover gates and the bridges. These are processed into 3DI input, and we prepare the 2D domain, mainly elevation, rocknet, and infiltration subgrid. For the rainfall, we perform frequency analysis to estimate the rainfall for different return period, and from this station, and this is the design storm distribution pattern for the hourly rainfall distribution. And we have 5 boundary condition, discharge boundary condition, and 1 water level boundary condition at here. And we simulate we select the scenario in 27 in total by considering the rainfall over the area. We have different kind of return period and the type from the sea and the discharge from the rivers. So these are the example. This is the example output map. So we have indentation map for a different kind of scenario. So this is the example map of the possible worst case scenario for Yangon, which is the spring tide, high tide, and high river discharge, and the 100-year return period design storm. So in this case, we can see most of the floodgates are blocked due to the high river water level in the river, and most of the area in the city are inundated from the river and the rainfall. So we can see some areas are flooded from the river, overtopping, and these are the area kind of like having the drainage problem. So this is the model developed in 2019. So my research work is considering the data resolution, how to integrate in the model to consider the need-based solution for the city. So Yangon has a very high urbanization rate, which caused the higher runoff, which got the higher rate runoff. So to mitigate, we can consider the higher dike, providing higher dike, more capacity ban. But these are the very expensive solution for a city like Yangon. So we need to consider the natural system to mimic and reduce the runoff. And also in Yangon, we also can see some example with the need-based solution. So for example, we have some practices, household level rainwater harvesting, and community level rainwater retention, and double use of the drain in some summer season. And we also have 2 lakes in the city, which serve as a retention function in the city. So I currently looking at currently working on the 2 things. First is to identify the potential location of the need-based solution in the city, and then the next one is how to integrate the need-based solution in the developed model. But I won't talk about the first things in this presentation. The general concept of the need-based solution is for the flood mitigation is the attenuation, harvesting the rainwater, and infiltration, and conveying the water slowly to the surface. So it is important to consider the storage simulation of the storage capacity of the soil, which is the unsaturated zone simulation, which can to see if the layer can perform the failing slowly and release gradually afterward. So I am trying to explore the simulation with the interflow layer in the 3DI. So in 3DI, the interflow layer is simulated mainly by the 3 parameter: porosity, thickness, and the hydraulic conductivity to calculate the storage capacity and the flow of the layer to simulate both soil filling and emptying. So among model, I choose the pluvial model, which has only rain without without high tide and high water level in the river. So tide and the water level are constant in the river. So I try to see explore the simulation in the interflow layer with the 2 rainfall distribution. First is the 10-year return period rainfall and 100-year return period rainfall. So I simulate with different cases. So this is the graph is to show the simplified IDR on the cases. So case 0 is a no interflow layer, and so the rainfall is the rainfall volume for the overall model area. The model area is around 200 square kilometer. So the idea is to see some flooding in every cases except this case 1. So the orange bar is the expected storage in the interflow layer. So I expect some flooded area in the other cases. So this is my first simulation with the interflow layer. So in the developed model, there are only infiltration and the rough net for the to simulate the model. I didn't include here, but I tried to simulate with the infiltration layer, which work well. It responds well with the infiltration layer. So I try to see the I try to see the simulation in the interflow layer. So these are the simulation that I did for the first as a first simulation. So for case 1, we don't see any flood as I expected, but I can only see the flood inundation area only in case 5 and case 6, but not in the other cases. it means the interflow layer store more water than I expected. So if we look at the volume balance for each cases, I can see that the model respond very well to the model respond well in the initial storage in 2D surface domain, but I can't I don't see the relation between the interflow layer and the change in the storage. So we in my model, is still there are still many higher in the outflow than the water inflow. So so this is the ongoing work, and I still need to explore more to understand the response of the model in the interflow layer simulation, and afterward I will make the simulation with the spatially variable parameter according to the soil type of the city, and modification in the infiltration layer, and the infiltration rate fine in the raster fine. It worked well to give the output of the model, and in later stage I will try to modify the topographic layer to have the retention lake. Yeah, something like that. So thank you for your attention, and this is the today. This is for my today presentation. Or if you have any question, please let me know. Thank you.
Okay, thank you very much for your presentation, and also for being on time. Is there any questions from the audience that would like to make any questions? I'm not seeing it in the question panel and nor in the chat. So I have one question for you, maybe. If you can extend a little bit more on the calibration, especially on the validation of your model, do you had any water levels measures along the creek that you used to validate your model, or inside the town for a particular rain that has happened in the city, something like that?
Yeah. Thank you for the question. Yeah, during the development of the model, we didn't have the water level measurement to validate, but what we did is to check the event, which is a bigger event, which is in 2014 and 2018. So we check this kind of event to calibrate and validate. So we have some picture and of the flooded area, and which are the flood-prone area. Also, we check this kind of area from our output. So to compare the water flood prone area and the flooded area during that event. So we calibrate and validate that in this way. Yeah, unfortunately, we didn't have the measurement for the water level in the city.
Correct. Okay, yes, thank you. Well, I don't know, Nikki, we have in here one of my colleagues is very interested in your presentation. She will make one question.
I think I can use your microphone better, otherwise we get a zoom in, so I will come to your screen. It's super nice to see that you're using the interflow option. For me, it would be very interesting to know what kind of type of interflow you have used. We have 4 different types of interflow, and which one did you use and why?
For this one, I would like to. I'm using the type 4 currently, because I like to consider the same thickness for the interflow layer, because my consideration is the impermeable layer have the same thickness of the porosity layer and the interflow layer, and I would like to consider the lowest level of the cell in each calculation for the whole domain. So I'm currently using the type 4 interflow layer calculation. Yeah.
Okay, and we have actually one question from the audience, from Mr. Jose Operes. He is asking if will other nature-based solutions also be tested in 3DI? If yes, how?
Yes. Thank you. I'm looking at the question. Yeah. My current model is kind of more like a citywide. It's a bigger area. So instead of giving instead of seeing the how to say providing data resolution for the whole city, I would like to work on the simulation ability of the 3DI to work with the data resolution. For example, working with the infiltration capacity and playing with the elevation layer to have a retention lake, and also the storage in the storage capacity in the SWA. But finally, I will try to come up with the potential location with the potential possible data resolution. So I will mainly trying to see at the few options, for example, retention lake and permeable pavement, this kind of option. Yeah, I'm trying to for now I'm trying to look at a different option, but I'm mainly looking at this kind of option. Yeah.
Okay, thank you very much. And well, now I would like to introduce our third speaker, Mrs. Raychel Bahnick. It's her last day in the Netherlands, by the way, so I hope you have a very good timing here. The topic of her presentation is going to be the quantify of the impact of land subsidence on flood resilience in the Polder landscape.
Okay, yes, so I'm Raychel Bahnick. I'm currently at TU Delft. I've been working on this research project for about a year now. I'm doing a fellowship in the civil engineering department, and I'm going to be presenting on it today. And it's quantifying the flood resilience in a Dutch polder under land subsidence. So my talk will be broken down into 4 parts. First, I'll go into background of my study and my main goals, and then I'll dive into my methodology. And then next, I'll talk about my 3DI model setup. And then finally, I'll discuss some preliminary results I found. So a little bit of background. The goal of my project was to utilize a hydrodynamic model, so this being 3DI, to utilize the output to quantify flood resilience, and then to measure the impact of future land subsidence on flood resilience in a polder. So my study area is the Balservaart polder. It's about 400 square kilometers, very large, and it's out east of Rotterdam. And my model domain is within this larger polder, so it's outlined in red. It's about 6 square kilometers, and it is land uses mostly for agriculture, but it also has a small town of about 1,200 residents. And the dikes in the polder are about 3 meters high, and the entire area is very low-lying, as most of the country is, but this area is about 1 to 2 meters below mean sea level. So now to discuss the methodology. To project future land subsidence, I first had to analyze historical data. So I had 2 LiDAR data sets from 2007 and 2020. And I first was going to subdivide these data sets into 135 water table areas. This was to get an average or a localized subsidence average rate, instead of just getting one value for the entire Balservaart polder, to get a more local average. And then next, I linearly extrapolated using some Python scripts as well as GIS to project 2070, 50 years into the future. And then this future subsidence was what was used as my DEM in my 3DI model. So based on the historical data of 13 years, the average subsidence rate within the Balservaart polder was about 3 to 4 millimeters a year. And the higher subsidence happens more in the middle of the polder, which is also where my model domain was. And that was closer to 8 millimeters a year. And then projecting out to 2070, this would result into about 3/4 of a meter of subsidence by 2070. But then in my area, which is this inner, more higher red subsidence area on the map, that's closer to 2 meters of subsidence, so pretty significant. And the historical data was pre-filtered, so it removed anonymously high elevations, including dikes. but my future 2070 DEM included dikes, so I lowered the present day terrain by this subsidence difference that I projected. And so next I'm going to talk about my framework for quantifying flood resilience. I got this from literature, and the definition for resilience for this study is the ability of a system to absorb and recover from the impacts of a disturbance. So the first thing to define is your Q of T, which is your performance measure. So for this study, dry area was chosen since it's something you can get directly from a hydrodynamic model. And then the resilience loss, which is able to be quantified by this shaded gray area, is the degradation of performance of a system or community in time. So mathematically, it's found by integrating to calculate that shaded area, and it's difference between like a fully undisturbed model or undisturbed scenario. So that's when the line stays straight at 100, it's a fully dry polder. And then if the entire area was flooded, then it would get to 0, and then you'd have a fully inundated polder area. So this difference is how you find the resilience loss. And then this framework was really useful because you can quantify several different things, such as your time to recover, and as well as your recovery rate, which is the slope of the line, and then resilience loss, like I mentioned. And the time to recover is the time between the disturbance, which for this study was a dike breach at T0, and then T1 is whenever the system is back to fully recovered. And then this framework also allows you to have different states. So the original state is pre-disturbance. And then once the disturbance happens, then you're into a disrupted state and a system recovery state. And then finally, you're in a fully recovered state after T1. And an assumption I made for this project was that the difference between the disrupted state and the recovered state is whenever the average depth across the model domain became constant in time. So that was when I assumed the dike breach was fully finished, and then now we could begin recovery by pumping out the floodwaters. And so yeah, the time needed to recover is that difference between T initial and T1. So now I'll talk about my 3DI model setup. So I had several different raster inputs. I used infiltration and friction, as well as my DEM, my terrain. And then my boundary conditions was a return period of 100 years. And this is because that is the design of those specific dikes in the polder. And then my flood event was a dike breach. So it happened 4 hours into the simulation, and it was 10 meters wide and 3 meters deep. And in red, you can see where the dike breach was put in to the model domain. So it's close to this city that's in the polder. And it's also at the lowest point in the levee. So it's where the water would overtop first. My resilient strategies put into the model were first trying mobile pumps. These were put in as laterals. So they're just sinks from the model to take out at a rate of 1 meter cubed per second. And then also a flood barrier. So this would maybe be an inflatable flood barrier or sandbag, something to capture the water. And that was about 1 meter high, and it was put in as an obstacle into the model. So here are my scenarios that I ran. There's 8 of them. So 4 of them I did for present day terrain, and then 4 with 2070. And I was testing these different resilience strategies. So under no interference or no intervention of resilience strategy, and then with the flood barrier, with the mobile pumps, and then trying these 2 strategies together and seeing how that would affect flooded area or dry area. So now I'll discuss some of the results I've found so far. So like I mentioned, recovery was assumed once average depth in time is constant. So this is showing average depth in time. The simulation ran for 5 days, so 120 hours. And you can see that the flood barrier significantly increased average depth of water. This is pretty expected because the water just stays within the flood barrier and doesn't overtop the 1 meter height of the obstacle. But without the flood barrier, the water disperses across the polder. And this is without subsidence. And so, yeah, the average depth is around 20 meters with a flood barrier, or 20 centimeters with a flood barrier, and then between 10 and 15 centimeters without. This is quite different when you have subsidence. It significantly increases the average depth after a dike breach. So with the flood barrier, it can get up to, in time, about 80 centimeters on average. And then we also have the pumps that significantly reduces the average depth closer to 50 centimeters of average depth. And then the without the flood barrier, it's significantly lower, but still much higher than without subsidence. So a big impact of subsidence is increasing average depth of the flood. So then here is discussing some of the resilience strategies. So in black, you see this example of having no disturbance. So this is like 100% fully dry scenario. And then in blue, you have in 2020. So whenever you have no intervention is in the solid line, and then using mobile pumps. So this is around 2 square kilometers of flooded area or less dry area. And then in red, you see in 2070, it's significantly increased. It's up to almost over 8 square kilometers of flooded area. And then you see the dike breach happens at 4 hours. And so at these sharp increases around 80 hours is when recovery begins. So that's when the average depth became constant in time. And then we assumed the water's pumped out. So this resilience loss is like this shaded area between the no disturbance and then these disturbances and recovery. And so it's much bigger with subsidence, which is an interesting finding. And then this is with the flood barrier. So before you saw like between 2 to 8 kilometers squared of flooded area. This is like a much different scale. So it's less than 1/10 of a kilometer because all the water stays within the flood barrier. But still you can see that the subsidence lowers or increases the flooded area or lowers the dry area, which is significant to note. And then there's some recovery within the system, but most of it happens after 40 hours once an average depth in time is constant, and then the forced recovery has happened for the assumed. So I mentioned that the flooded area is so much more with subsidence, and so this is showing like the floodplain extent from the model output. So whenever there is no subsidence, all the water stays in the polder but just gets quite deep. But then whenever there is subsidence, it's enough that projected subsidence in 2070, the opposite dike is lowered enough that the water is overtopping it and flooding the opposite polder. So that's an interesting finding. And then to highlight these figures in table form, subsidence significantly increases the flooded area by over 3 times, which is what we saw in those graphs before. And then the flood barrier also nearly doubles the average depth. And that's expected because the water stays within the flood barrier. And then subsidence significantly increases average depth by 20 to 30 centimeters. So that's an interesting finding, seeing how subsidence would impact flooding in the future. And then these different resilience metrics we had, which were time to recovery, resilience loss, and recovery rate. The flood barrier minimizes resilience loss and recovery and time to recovery because it would dramatically reduce the flooded area. So that was, since that was our performance measure of using flooded area, that's where you found the big difference in resilience loss. And then we also found that subsidence made recovery time much longer and increased resilience loss. So this is especially for the no intervention scenario. And this is also because of the flooded barrier and also the dramatically deeper depth. So it took much longer for the water to be pumped out if the pumping rate was at a constant. So that's some of my results from my project so far using 3DI, and I'm happy to take any questions. No, did you all hear me?
Okay, thank you very much. Yes, I was looking for a charger. Thank you very much for your very interesting question, Rachel. So do we have some questions from the audience? Basically, yeah, we have a question from Benjamin van der Waal. He's asking how what is driving the subsidence in the sector?
Yeah, so that's mostly because they are mostly used for agriculture, and so they keep their water levels pretty low because they have farming, and the soils are mostly peat soils. So this lower water level results in drying of the soil and then in further subsidence. So it's a balance between keeping the water levels at a certain height that the agriculture can still continue, but subsidence doesn't get too severe.
Okay, perfect. Then we have another question in the panel from Thomas Thelen. He's asking about if you have noted any potential drawbacks to assuming a linear extrapolation for future subsidence. Are these reasons we might expect subsidence rates to change between now and 2070, basically, if instead of being a linear, it's like something different?
Yeah, that's just, I think it's really dependent on policy changes within the water boards and the local area. I'm not sure exactly like if they're planning on changing these regulations in the future, but this is assuming, yeah, this historical data will continue, which, yeah, it could be a very extreme case because hopefully there's noted and there's a lot of reports about subsidence in this particular polder. So with awareness, hopefully regulation will be more impactful in reducing subsidence.
Okay, finally, we have also another question in a chat. It is about the infiltration also contributes to the recovery. Did you keep that constant? And is there any effect expected to the infiltration capacity in case of such strong subsidence?
Yeah, so I was hoping infiltration would have a greater impact so that I wouldn't have to force this recovery with just pumping. But because this area is so flat and it's all enclosed by dikes, the water just pools and stays where it is, it doesn't drain. So I think that's a limitation of the study site. And so even I ran the model with, as far as 2 weeks long, there still wasn't any like significant influence by infiltration. I didn't increase infiltration over time. I just kept it by my initial inputs. So yeah, I think maybe if this was maybe in a place that had a more drainage ability, and instead of just having to pump out the water, you would see this recovery happen without having to assume a linear recovery with constant pumping rates.
Okay, maybe we have time for the last question, and then at the end of the presentation we can have host more questions for you as well. So Mr. Josea Opedes is asking about, well, he's saying interesting results. Is subsidence only in the study area, or it affects adjacent environments? Environment, I suppose that he's mentioning other adjacent basins as well.
Yeah, no, there's a lot of subsidence happening in different parts of the Netherlands. This area is notably significant subsidence rates, but not the highest for the country. It's more intense even in the north, in Groningen, that has a different cause of being extracting gas, but there is, yeah, subsidence in different parts of the Netherlands outside of the Wasserwaard polder.
Okay, thank you very much, Raychel. Maybe I will have also a question for you. Then our last presenter is Mr. Thomas Thelen. He's going to talk about the 3DI couplet with an ocean scale hydrodynamic model.
All right, my name is Thomas Thelen. I'm a graduate research assistant in the Department of Civil Engineering at NC State University. And today I will be presenting an application of 3DI coupled with an ocean scale hydrodynamic model to simulate multi-driver chronic coastal flooding. This work was developed with my advisor, Dr. Catherine Anardi, and the rest of the Sunny Day Flooding Project team. So as sea levels continue to rise, coastal flooding is happening more often worldwide, even in the absence of extreme storm events like hurricanes. In the GIF up on screen, a half-inch rain event that coincides with high tide causes flooding in Carolina Beach, North Carolina. While these chronic floods do not get as much attention as flooding from hurricanes, they do have real-world impacts. In this yellow box here, you can see garbage cans float away in the floodwaters and spill trash. And in this blue box here, a car stalls out and has to be towed out of the flood. So I'll let this GIF play through one more time here, in case anyone missed that. All right. Researchers have started to quantify some of these impacts to individuals, infrastructure, and businesses. For example, along the east coast of the US, there are 7,500 miles of roadway where your car might stall out, and 2 million people whose trash cans might float away. It's also important to note that these are present day numbers. these floods will only become more frequent and intense with future sea level rise. Current methods for modeling and forecasting this coastal flooding, like bathtub modeling, do not consider the compound drivers that can contribute to flooding. However, multi-driver floods, like the rain at high tide example up on screen, do pose a hazard to coastal communities. A 2023 study by Gold et al. Found that 25% of floods in a coastal North Carolina town occurred during rain events. In this talk, I will present a coupled model framework that we are developing to simulate these hyperlocal, recurrent coastal floods from multiple drivers. I'm going to start by briefly overviewing the type of flooding that our group studies and the sensors that we use to collect data for model validation. Our group has developed a novel sensor to detect floods at roadway flooding hotspots by measuring water levels in storm drains. The Sunny Day Flooding Sensor, or SUDS for short, is a two-part sensor. A pressure logger in a storm drain, here, records water levels at infrastructure that's prone to flooding. A communication gateway with a camera mounted near the drain captures images to validate the spatial extent of water levels. SUDS capture flooding from the ocean, just like a tide gauge would. You can imagine this flooding overtopped the bulkhead here or came up through the stormwater system here. Either way, it is captured by the SUDS in the storm drain. But because SUDS are located within stormwater infrastructure instead of in the receiving body of water, they also capture flooding from land-based sources, like the rainfall example I have up on screen. SUDS are deployed in 3 partner communities in North Carolina. This presentation will focus on the town of Carolina Beach. This town is the focus of my PhD and the first location where we're developing a model to simulate flooding. We installed the first SUDS here back in February 2022. Floodwaters in Carolina Beach move from the harbor here to the roadway here, over land or via the stormwater system, when water bubbles up through storm drains and spills out onto the road. To simulate this flooding, I'm developing a coupled hydrodynamic and stormwater model of Carolina Beach. In the hydrodynamic model at CERC, we simulate ocean scale processes that drive local water levels, including tides, wind setup, and future sea levels. Our AdCERC domain includes the entire Western Atlantic Basin here to fully represent tidal propagation and wind setup that can drive high water levels along the North Carolina coast here. In our model, tides are forced at the eastern ocean boundary, while atmospheric forcing, including wind and pressure, is applied over the entire mesh domain. In the much smaller 3DI model domain, we simulate localized flooding drivers like rainfall and runoff, infiltration, surface water flow, pipe flow, and local adaptation measures that the community might consider adopting, like raising shoreline elevations or adding wetlands. To couple the models, we take water levels calculated by water level time series calculated by AdCERC at the water bodies around Carolina Beach, here, here, and here, and apply them as 2D boundary condition forcings in our 3DI model. With this approach, we have a one-way coupling from AdCERC to 3DI. I first developed the AdCERC simulations, calibrating the model against a water level gauge in the Carolina Beach Harbor. This is a water level time series from May 2022. On the y-axis are water level in feet. Sorry about that for y'all who are familiar with meters, but basically 3 feet is about 1 meter. In blue are water levels from a gauge in the Carolina Beach Harbor, and in orange are modeled water levels from AdCERC. From May 10th to 13th, water levels above the edge of road elevation, which is how our group defines flooding, result from an offshore low pressure system and winds that push water onshore. Here, the whole tidal cycle takes place at higher than normal water levels. On May 15th through 19th, we see flooding from a different driver. Water levels are above the road elevation due to king tides. Here we have higher than normal high water levels, but also lower than normal low water levels. We note that AdCERC accurately simulates peak water levels and timing with slightly better performance for tidally driven events. This is the same plot, but with water levels measured by a SUDS and a roadway storm drain in green here. When the green storm drain water level line goes above the roadway elevation in red, we have flooding on the roadway. I want you all to note that the stormwater system distorts the tidal signal in the storm drain, such that peak water levels on the road lag peak water levels in the harbor. I also want you to notice the inflection points where we have a rapid increase of water levels in the storm drain. The town has installed duckbills, like the one pictured here, on stormwater outfalls that are supposed to keep water in the harbor from backflowing from the harbor into the stormwater system and out onto the roadway. SUDS data show that these valves are only partially effective in preventing flooding. They can hold back water temporarily, but elevated water levels in the harbor, duckbills no longer prevent flooding. This may be because floodwaters can bypass duckbill valves by overtopping low-lying shorelines and moving overland to the road and stormwater system. Difference between water levels in the harbor and on the roadway is a motivation for using 3DI. The 1D, 2D simulations in 3DI are well suited for resolving the magnitude and timing of flooding that moves from an open water body through stormwater infrastructure or overland to upland areas and roadways. Because 3DI is a subgrid model that retains the bathymetries and topographies of the input elevation raster, this model allows us to resolve flood extents at the 1 meter resolution of our input digital elevation model. Up on screen, we have a drone image from another flooding event in November 2021 and modeled floodwater depths from the corresponding time step in 3DI. The drone image and the 3DI flood extents agree that water extends halfway up the box parking lot at this time step. In addition to looking at flood extent, we can also use a coupled AdCirc and 3DI model to assess the contributions of tides, rain, and atmospheric effects like wind to flooding water levels. The water level time series from a flood on January 22nd, 2023 shows measured and modeled water levels from a storm drain on Canal Drive, a flood-prone roadway in our study site. On the y-axis are water levels in meters this time, relative to the NAVD 88 data. The background shading shows measured rainfall intensity, and the dotted lines show water level measured by our storm drain sensor. The dash line shows coupled model results from the same storm drain for a simulation with forcing from all three flooding drivers: tides, atmospheric effects, and rain. When water levels go above the black roadway elevation line, there's flooding on the roadway. I want you to note that model results and measurements show similar flood magnitude and timing. We can extend this analysis to assess the individual contributions of our three drivers by running simulations with tides, rain, and atmospheric forcings turned on and off. The GIF up on screen shows the same January 22nd flood, but the coupled model simulation only includes tidal forcing. Atmospheric and rainfall forcings were not turned on in this run. I want you all to notice that while the boxed area at the top of this GIF is overtopped and flooded, the simulation results indicate that tides alone would not have caused flooding to reach our sensor on Canal Drive. But when we turn on atmospheric forcing in our flooding model, we see a different story. The contributions of tides plus atmospheric effects, namely wind, push water levels high enough that they move around the corner to our sensor on Canal Drive. The simulation with tides, atmospheric effects, and rain shows similar results, but with slightly deeper flood levels from the additional rainfall runoff. By hindcasting events with different combinations of flooding drivers activated, we can quantify the contributions of tides, wind, and rain to flooding at our study site. Now let's examine the time series from the January 22nd flood one more time. While the maximum flood depth and the falling leg of the flooding simulation results match water levels measured by our flooding sensor, there's a discrepancy here in the rising leg of flooding water levels. Measured water levels in the storm drain increase later than simulation results might indicate, because duckbills initially keep water from backflowing into the stormwater system. I'm currently developing control structures in 3DI to replicate the way duckbills moderate water levels in the stormwater network. The coupled model approach I have just talked through is a framework for simulating multi-driver coastal flooding at spatial and temporal scales appropriate for this hazard. The 3DI subgrid method resolves flood extents and depths at a resolution that captures flooding on the scale of city blocks. The ADCIRC portion of the coupled model simulates ocean-scale hydrodynamics that drive water level increases along the coast, while the 3DI portion captures localized flooding drivers and infrastructure impacts. Once we have a fully developed coupled model calibrated to data from our sensors, we will use this model to simulate future flood hazards by running simulations at different future baseline water levels as projected by sea level rise forecasts. We will also engage the community in a participatory modeling framework to see what adaptation pathways they might want to pursue and test the timescales and levels of future sea level rise at which these adaptation measures will effectively mitigate flooding. That's all I have for you all today. Thank you for your attention, and I would be happy to take any questions.
Okay, thank you, Thomas, and thank you also for your maintaining the time. A very nice presentation. I will try to see if there is any questions in the panel for you. I think there are none questions now, and in the chat there are also no questions. So I can proceed with one question in a parallel chat I have. Yeah, so Nikki here is asking about the coupling with that ADCIRC model. Is a one-way coupling. Do you think it will change your results significantly if it will be a full double coupling?
Yes, so that's a good question. The question was, would a two-way coupling significantly change between ADCIRC and 3DI significantly change our results? Our assumption is that it would not. The assumption is that the water inputs that we're adding in 3DI, which is namely rainfall, is minor compared to the water movements that we're simulating in ADCIRC. And part of the reason for that assumption is that it would be difficult to go back and forth between an ADCIRC simulation and a 3DI simulation and have them talk to each other and exchange water in real time. Though with the one-way coupling, we can run our ADCIRC simulation and then take our ADCIRC time series and input them into a 3DI simulation run. We don't have to have the models talk to each other. And so far, we found that one-way coupling seems to hold up in terms of 3DI water levels match ADCIRC water levels for the same location in the harbor. So it doesn't seem like developing a two-way coupling would be worth the additional simulation and setup time that it would cost. Did that answer your question?
Yes, I think so. Yes. Here at Masai. So actually, I have also a very similar question. Does these events you are analyzing, like they are, I mean, or maybe let me resentence. Have you analyzed what could be the influence of the wave height? Because basically with ADCIRC, you are not simulating wave height, and in the coupling, you are going usually with water levels. But then I was seeing your graphics and they are fit pretty well. So there is not like underestimation of the water levels, basically, that in other kind of storms could be because the wave are not simulating, basically. Can you have a small comment on that?
Sure. Can you all still see my screen here?
Yes.
Yes. So I think your question was about simulating waves in ADCIRC, and It's a very good question. So the way that floods occur in Carolina Beach is the flooding doesn't come from the open ocean here. The land is actually lower on the harbor side, so floodwaters move from the harbor, which is sheltered, to the roadway. And we've run ADCIRC simulations, ADCIRC and SWAN simulations, where we do include wave setup in our model, but we haven't noticed, or when we compared the harbor side water levels from our ATCIRC simulation and our ATCIRC and SWAN simulation, we found basically no difference. Just because it's a sheltered area, and although if there is wave setup, it's happening out here in the open ocean, and by the time those waves reach the harbor, they're basically negligible. The other important thing to consider here is a lot of this flooding happens during low wave conditions. We're not looking at hurricane type storms where we have large wave setups. We're looking at high tidal events or combined rainfall and tide events, or maybe an offshore low pressure system with some wind that results in a little bit of wind setup, but really not as much wave setup. So we found that waves aren't an important part of the chronic flooding here in Carolina Beach.
Okay, very nice. I have actually a second question. If no one else is having more questions, let me see. Yes, yeah, but my second, more than a question, is like an observation, because I found like very innovative. You are using these cameras to detect the floods, and also the pressure sensors to measure the water levels. And I wanted to ask you if you know about this open source Python package called Open River Cam, because once you have the cameras, you can install these Python packages. And basically, if you have a camera, then you can also calibrate to measure flow velocities. That later on is another parameter you can use to validate your model.
No, I have not heard of that Python package. What did you say it was called?
It's called Open River Cam. So maybe it's something you can also try it off, because then you will have also the flow velocities at that point, you know. It's basically just only you need a camera. It doesn't need to be a very expensive camera with a special lens or something like that. And then just only under some parameters you calibrate these packages, and then you can have basically the flow velocities. It's a very nice open source package.
Yeah, that's a good suggestion. I'll definitely look into that. Thank you.
Okay, so let me see. I think in the chat we have another question for Miroslava. If you have compared economically what of your mitigation measures, green, blue, gray, is the best to mitigate flood events for your case study? Do you made any economical assessment on what could be the best option to implement? We cannot hear you, Miroslava.
Okay, now, no, I didn't compare it. It wasn't my task. My task was only compare the way how would the water absorb, would it be stored, not from the economic side.
Okay, thank you. Okay, so is there any other question from the audience that anyone wants to ask? If not, I think we can finish practically half an hour before, because one of the presenters.
I think we also would like to discuss some of the wish list.
Yes.
And if there are any experiences that you would like to improve, but we can finish the questions and then we have some time for that.
Okay. Yes, so just a couple of more seconds. Let me see. No more questions in the chat. No more questions in the. Okay, yes. So maybe to ask you, and also for the audience to know, maybe we can start with Jay. How was your experience using 3DI? What kind of comments do you can give to us about our model and your experience in general? What can you tell us? Yeah. Yeah, sorry, maybe I'm mispronouncing your name. We cannot hear you. Yeah, now.
Yeah. Yes, I am. So far, it is a good one, because I once before that, my first experience with 3DI is in 2019. So when I use now is again the interface is really improved, and which is very easier to use compared to the 2019. Yeah, so I'm very happy with that. And yes, a bit for I don't have I can think of immediately, but I have some difficulty in producing the measurement water depth after the simulation, because I don't have a lizard. But I think I can have that kind of function in next month or something like that. I heard from the Subsidence. So yeah, it's good. Yeah.
Okay, thank you very much. Yeah, maybe as a general question for all of you, yeah, Raychel, Thomas, and Miroslava, how was for you the procedure of building the mesh? It was easy, and maybe if you have some experience with other models, can you tell us also a little bit about like that experience using the 3DI compared with other models? Any of you? I don't know who wants to start.
Yeah, I can talk a bit. I've had experience with one other model that I think the other model took me a lot longer to build the mesh, because there are a lot more errors over time that I had to like manually fix. With 3DI, my study area is pretty small, so it didn't take very long to build the mesh without errors. I will like echo the similar problem I've had with which is related to the mesh, is that I had to keep my mesh regular. I wasn't able to refine in areas because of my results analysis. I needed to compute like every single time step the average depth or flooded area. So I didn't have the lizard account either. So to do that, I had to like build my own script to use the output file to look at it in time. And I wasn't able to like figure out how to do that with an irregular grid. So yeah, I think maybe if there's some other way, I guess maybe to get depth outputs with an irregular grid, but like, you know, I need like every time step for 5 days. So it was a lot of output files I needed to make. So I found a way to work around it, but I think that was a limitation of my model because of not being able to get depth rasters easily.
Okay, I'm noting here.
But I think you can get them from the model interface as well.
Yeah.
So it
just would take a long time.
Sorry?
Sorry. Well, I need it every time step, so I wanted to make a script that would make it happen very quickly, instead of having to go manually and do. I know there's a way to output a depth raster, but like I need like 200 of them, so it would have taken a long time rather than making a script. Maybe I'm also limited in my coding, so I think maybe there's a better. I could have made it work, but
I would echo that a little bit. I also created depth rasters, like for the GIFs I popped up. Those are just a bunch of depth rasters calculated. And the big challenge in creating those is if you want to run a batch process, it seems like the batch process functionality in the modeler interface is tricky to use, and that you almost have to set up every step in like the batch process that you want to run. I kind of found a bit of a workaround where I made my own Python script to run within the modeler interface and like the QGIS Python GUI, or however Python and QGIS works. And I kind of worked around the current batch process thing, the way it's set up there, just because it, like Raychel mentioned, the calculations of the depth rasters take a long time, and I think maybe there's just no way around that because there are a lot of calculations that go on behind the scenes. But two, it's hard to tell like what time period and intervals you want to calculate those depth rasters at in the modeler interface GUI. But on the whole, I would say setting up a model in 3DI, I really liked working in QGIS. It was a pretty intuitive interface for setting up your model and then sending it to run on the cloud. The biggest challenges, like others have noted, are probably in post-processing, especially if you don't have a Lizard account. One thing that has been helpful are the Jupyter notebooks for like obtaining water level time series and nodes. Those have been really useful and pretty easy to modify for our own uses.
We are actually looking for a place where we can share our scripts that everybody made, because lots of the requests or scripts that, for example, Raychel needs, that we are looking for a way how we can share them. If you are willing to share them, of course, because then we can build up a little bit of a community in it. It is something we have on GitHub. We can send the link and put it on the website a little bit more clear, because I think it is nice, because lots of scripts are available, made by lots of people everywhere, and we're a little bit looking at how we can maintain them, or whether we need to promise you that it will work, but as long as it's not made by us, it's a bit difficult. But so if you're willing to share your script and have a little bit of explanation with your script what it does or what it should do at least, then we can help each other with that. So that would be super nice.
Yes, thank you. And finally, maybe Miroslava, do you have any comments about working with the 3DI? Any?
Yes, there was one thing what I wanted to tell you. I had a problem to connect my model with the pipelines because I already had it with attributes. Unfortunately, it was for me impossible to integrate it, because when I connected with your support center, they told me that it could be connected by using SQL of the program. Unfortunately, my SQL skills are not good enough for it, so I left it. And I wish, or maybe it could be useful for you, that even this part of the program would be as easy as the other ones, because building 1D model of river was pretty easy, and it was really sad that I couldn't connect pipelines as well.
Do you go also through the documentation and you didn't manage to find anything to explain that, correct?
Correct, yes. I looked at the documentation and so on, but yeah, unfortunately I didn't get it, so I couldn't really compare it how it looks it's in reality. Yeah, that's the only thing. Nevertheless, it was, as others said, it was easy to use it when you know how to use QGIS.
I'm sorry to hear that it was a bit complicated. We have improved the last few months quite a lot, the editing features, because especially for the 1D thing. So that might be that it's now a little bit better than before. And we're also working a lot on the documentation. And if you have certain aspects that are unclear in the documentation, we're of course, actually quite a small company. So if you have requests on what should be explained better, please let us know, because it helps us a lot to prioritize what should be done. So please feel free to tell us that, and then we can try to prioritize our updating of our documentation. And I think the editing tools for 1D has been improved a lot since the last half year. So I'm not completely sure anymore when you did your modeling work, but it might be easier by now.
Okay, yes, so then from our side, I think we don't have more questions. Maybe as a closure remarks is, especially for the audience, if you got interested, please go through the documentation we're going to send. So basically it's the presentation I was showing in the beginning. In there, you can find the link on how to request an academic license if you're interested. So actually, I can show it quickly. Yeah, basically, you can go directly to the page www.3diwatermanagement.com. In there, you can have in one of the deployables a section called 3DI4 and then scientists. And then if you go through the explanation of the web page, basically you will see, sorry for that changes, you will see what are the requirements to apply for a 3D academic license. So basically, we are very open to researchers to use our model. Of course, as far as the model is not going to be used for commercial purposes, we are almost always saying yes for an academic license. So basically, that is the requirement, and you can find in there how you can apply, which is very easy. It's usually sending an email with some questionnaires and answer some questions. In there, you can also have some documentation of the model and some tutorials that we have created. And this is what Nikki was explaining before, that we are constantly updating this documentation, these tutorials. And of course, we are also always willing to receive comments on whether we should extend a little bit more and so on. So yes, we are very welcome. So please, if anyone else in the audience is interested to ask for an academic license, you can apply. We are always waiting for that. So I think this is very much all. I want also to say thank you to all the presenters. Your topic has been very interesting.